Okay. Let's talk about chapter 6, thermal energy. Now, there's certain parts of this chapter I really want to focus on, and that'll be towards the end of this, doing some calculations similar to what we did in lab. Okay, the amount of kinetic energy in an object is directly proportional to mass and velocity. Many of you have heard of mass is equal to 1/2 mv squared. So it's proportional to that. That means directly proportional. It's also directly proportional velocity squared. Okay. And kinetic energy, the metric we use for kinetic energy in chemistry is temperature. And that is in Celsius or Kelvin. Kelvin is the absolute temperature, and the units are centigrade. Okay. If we stick to our standard units of kilograms and acceleration or velocity squared is m squared over second squared, we end up with a joule. So a joule is going to be our, which is abbreviated J, nice abbreviation. Our standard unit of energy in this course, or kilojoules. Okay, other standardizations are using calories. Okay. All of you have heard of kilowatt hour on your electric bill. This is what they're talking about, is energy used per hour. Okay. First law of thermodynamics. Okay, thermodynamics to start with. Gosh. Thermodynamics is a study of energy and its interconvergence between kinetic and potential. We have many laws in thermodynamics. First one is conservation of energy. That means the overall energy of the whole system doesn't change. Which means we can't invent energy or finding a source of energy. There has to be a give and take. There's a term called internal energy, which is the sum of the kinetic and potential energies that compose the system. Okay, a new term here called state function. It's basically what we start with and end with. So basically in a reaction, we've got products and reactants. The net energy of that reaction is the sum of all the products minus the sum of all the reactants. And this is important. As reactions, chemical reactions usually involve more than one product and more than one reactant. So if we look at the creation of carbon dioxide as an example, we are looking at taken the negative of negative change in reaction equals the change to the surroundings. In other words, if something happens internally within that chemical reaction, it's reflected in the environment in an opposite way. So if that reaction creates heat, it's got to give heat to the environment so that it's on equal footing. If the reaction requires energy, then it pulls it from the surroundings. Hence, it'll get cooler to the touch, for example. Okay, energy diagram, as we're showing reactants and products. And normally, it looks something like this. We have at a certain level of energy. And then we have a product here, and this is time. In this case, we have a net negative energy in the system. And this will be considered the exothermic reaction. Okay. All right, energy exchange. Okay. We, and again, remember that the energy in a molecule is going to be a combination of work energy, the vibration or movement, plus thermal energy in terms of heat. Okay, and that can be expressed in terms of potential energy of the bonds. Okay. Kinetic energy can be further broken down into work done by a system and loss or gain of thermal energy. So what we normally do when we do reactions, we consider the work to be done to be zero. So really the only value of thermal energy we're looking at is Q, or heat. Okay, these are, normally they talk about the exchange rather than just heat, and then parenthetically saying it's exchange of thermal energy. A heat exchange occurs when the surroundings have a difference in temperature, the system and surroundings. Then things will equilibrate, become more stable. Okay. As a metric for temperature, as a metric for heat, we're going to use temperature as a metric. And it's in many, many forms, the metric. The one we use in science is the metric system, which is going to be calories and Kelvin. Kelvin is an absolute temperature scale. Celsius is a relative temperature scale. Okay, for stability reasons, heat will flow from high temperature to low temperature until there's an equilibrium reached where the heat energy is the same. So if you put something hot, a hot piece of metal in a cup of water, what happens? Well, the metal object loses heat and the water gains heat until the temperature of the metal device and the water is the same. Okay, there are ways to calculate what's going on there. It has to do with the capacity of the two objects. Okay, heat capacity is how much energy is required to move the temperature. Something with a high heat capacity, like water, for example, takes a lot of energy to change its temperature. Or something like aluminum has a low heat capacity, and it takes less energy to change its temperature. Okay, so heat capacity depends on the amount and the type. So each different molecule has a different heat capacity. There's two kinds of heat capacities. One is specific, which is, the key word here is gram. So that's joules per gram per degree. And then there's molar, which is how much of a change with 1 mole of a substance. So mass and specific heat are the key elements for this. Calculate the heat in joules. Looking at mass times the heat capacity times the change or delta change in temperature. And this can be Kelvin also. Okay, specific heat of water is quite high. And it manifests itself in the world in many different ways. For example, when you get out of the shower, if you don't towel off right away, you get cold. That's because the specific heat of water is so high that it requires lots of energy to evaporate, in which case the temperature for that evaporation occur is coming from you, hence you get cold. Again, I mentioned when two objects, different temperatures are placed in contact with a good thermal conduction, like water, the temperature or kinetic energy from that higher temperature water goes down and the surrounding water goes up. We can quantify that by looking at thermal energy of 1, thermal energy of 2. That there is a change in thermal energy, they have to be equated. Okay, so the variables for thermal energy are mass of a material, heat capacity of that material, and the change in the temperature of that material. The other materials, in this case water, that's the water surrounding the middle, the heat capacity of the water, and the change in temperature of the water. So we have two devices changing temperature here. So the term enthalpy is just the sum of all the energy in the system. And enthalpy change, assuming this is equal to 0, is simply a measurement of the potential energy of the system. When delta H is negative, heat is being released into the system. Okay? So if you were holding a beaker of a chemical reaction and it got hot, that means the system U is receiving energy, kinetic energy in this case, from the reaction. So the reaction is sending energy outside of the reaction. The opposite is the reaction needs energy to progress, so it draws it from the surroundings. Endothermic. Think of endothermic, cold, exothermic, hot. And there's a lot of examples of that in your daily life. Cold pads, hot pads, etc. Okay. There's an exchange between kinetic and potential energy whenever a reaction happens. We can measure that change via the metric temperature. During a reaction, we talked about this a lot, existing bonds are broken, new bonds are made. That's called a chemical reaction. The products of a reaction usually have less potential energy than the reactants, most of the time. And we get to later on in thermodynamics, we're going to talk about entropy. And gives free energy. They are a more accurate measurement of this energy exchange. Okay, this is a nice summary of what's going on in an endothermic reaction. Basically, when all the changes have been made, they require energy from the surroundings. It means a pull in energy. Hence, if you're holding the beaker, it's going to pull it from your hand, which makes your hand feel cold. Now we can calculate the enthalpy of the H of a reaction. To do that, we're going to use a combination of reactions that add up to the reaction we're interested in. Additionally, if we change the direction of the reaction, the sign of the delta H will change along with it. Also, this is a molar relationship. So if the moles go up, the reaction delta H goes up proportionally. So if the moles go up by 2, delta H is multiplied by 2. And if the reaction is reversed, we change the sign of delta H. Now, Hess's law involves, if we don't have an overall delta H for a reaction, we can add up other reactions, and we can add up their delta H's as long as we end up with an algebraic equality. So the delta H of the reaction is equal to the delta H of the products minus delta H of the reactants. These come from tables. Okay, they're called standard enthalpies of formation. Formation means how do you make it? Okay. If you're making something that's elemental, you start with silver and then with silver. It's not really, nothing's going on there. Hence the zeros. Everything else has got either positive, excuse me, delta H or a negative delta H. These tables get quite expensive. Okay. And these are per mole of the compound. Okay, the formation reaction is product. How do we make it? Okay. To make carbon monoxide, we have one carbon, one oxygen uses one molecule of carbon monoxide. Or 1 mole of carbon plus 1 mole of oxygen gives us 1 mole of carbon monoxide gas. Against standard states, that's STP, which is 1 atmosphere, room temperature, 298 degrees Kelvin. Now, when you balance the equation, you have to balance it so the formation is 1 mole, which might require you to do fractional coefficients for the reactants. Any reaction can be written as algebraic sum of formation reactions, or the reverse. So the summation of the moles of products minus moles of reactants is the delta H of the total reaction. Now let's look at this reaction here. Methane CH4 is burned in an oxygen environment and it forms gaseous water and gaseous CO2. Now the idea here is we want to take the formation of the products and reactants and those subsequent delta H's to find the total delta H of the total reaction. Because we know the delta H's of the formations from our tables. The tables usually don't get a specific delta H for specific reactions because there are so many. So let's see how to do that. Again, remember, we have delta H of the products and delta H of the reactants equals total H of the full reaction. Okay, so basically, algebraically, I'm going to add up formation reactions that equal our product reaction. Okay, so let's look at these guys here. These again are formation. It's really important to understand that. In other words, how do you make calcium oxide? Well, it's calcium plus oxygen equals calcium monoxide. Okay, and these are all in kilojoules per mole. Kilojoules per mole. And remember, with a balanced equation, that we're talking about coefficients here. Okay, so let's just do this from scratch over here. So what we're going to do, we're going to add up the reactions of formation equal this reaction. So carbon dioxide and water are both being formed. So we can use the values straight from the table. Okay, so let's look at carbon dioxide. That's made from carbon plus oxygen. And that delta H is minus okay. Formation of water. And what? We want this always to be one. That's the definition of from the table. Coefficient of 1. So sometimes we have to have fractional coefficients. Okay, and that is kilojoules per mole. Okay, now we need the formation, the opposite formation of methane. Notice that's positive rather than negative. That means whenever it's positive, that means the reactant is very stable. Okay, and what else do we need here? We need created water. We've decomposed methane, and we need to see. We have this up algebraically. What have we got so far here? Well, think of these as simultaneous equations. We have, some of these are going to cancel. And okay, if we algebraically add this up, we're going to get CH4, 1CH4 plus 1.5 oxygens. Oh, this is not balanced. Okay. And here we have this 1 CO2 and 1 water. Notice everything's canceled over here. So is this the same reaction we're looking at up here? No, not. Okay. All right. Well, let's see here now. Notice we have 2 here and only 1 water here. So we're going to multiply everything here by 2. Okay, that'll give us 1 water here plus 1 water is 2 water, oxygens. And over here we have 2 times 1 is 2 waters. Okay. Now this, what we've done now is algebraically added up our equations or our reactions to equal what we wanted to start with. Now, notice here we have a 2 there. That means this is going to be multiplied by 2. Okay, so we're going to have, we add these up, we're going to end up with kilojoules per mole. Now these can be tricky at first because there's a lot of reaction going on, and we're actually adding them up algebraically so that this matches. Balanced equations match. And we get the same thing. Let's take another example. Let's take, instead of methane, let's look at ethane. Instead of gaseous water, let's look at liquid water. Okay, so let's balance this. Okay, so that's balanced now. 12 hydrogens. No, it's not done. Okay, so we have 10 oxygens, 2 oxygens, 6, 12 hydrogens. Okay. All right, so we've got to form these. And decompose these guys. So we've got and that delta H is equal to positive 8468 kilojoules per mole. The formation of water. Notice we have coefficient of 2. So make this 2 down here. Multiply all this by 2. Okay, because we want the balanced equation to come out down here. With the water, okay, liquid water. And that's made from okay, and how many waters are there? There are 6 waters. And the delta H for one of them is equal to minus 35.8 kilojoules per mole. Okay. Let's see, what do we have left over here? Carbon dioxide. It's going to be only 2 of them. And one of them is okay, so let's add up these equations algebraically. Let's rewrite these 2 guys. So first we start with multiplying 2 by everything. And that means this is going to be multiplied by 2 also. Okay. So it's going to be 2 times 84.68. let's expand this. So we have 6 waters plus 3 O2s equals 6 waters. So that's going to be 6 times minus 25.8. So we have so it's going to be 2 times okay. Let's add this guy up here. And we have 2 C2H6s. Let's cancel some stuff there first. Okay, we have 2 of those, 2 of those, 6 of those, 6 of those. Okay, so we have 2 methanes plus 5 waters. We have 6 waters plus 2 carbon dioxide. Now let's compare that to our original equation here. Yeah, okay. So this agrees. Now we just have to do the math over here. Okay, so we have 2 positive 8468s minus 6 258.8 plus 2. So 58 is there. So yeah. Well, 393. That's 15. No. 72. So that's the delta H for ethane burning. Okay. That's it on this chapter, okay? I want you to focus on the last part